is just the well logging guys, Schlumberger, Halliburton. They are coming up with some really good engineering to gather more data sets and gather different types of rock properties that can be used for lots of different variations. I'm mostly concerned with the stratigraphic and sedimentological characteristics that I can get from them. And so what is being run, there's always data sets, there's always something that could be used, whether or not it's useful or not to answer your questions or how it can be useful, then that's always the question that as us as geoscientists are trying to figure out, to sort out and go through and say, hey, this can actually answer my questions and reduce the uncertainty. Because in the end, we're trying to always reduce the uncertainty of whatever data set that we're working in through there. So we got tons of possible data sets that we can work with, tons of possible attributes that we can find. However, we have to remember where this is coming from, right? And what uncertainty is associated with all of those data sets, because not all data sets are created equal. Not all data sets is being measuring the things that maybe you need to be measured, right? So the way I break it down in terms of the data sets that you have is you have primary data sources, and these are data sources that have basically no or very few assumptions going into there. So these are basically direct measurements. When you go to the rock, when you bring out core, you can touch and feel it. You can get it down to elemental level, SEM photomicrographs, thin sections, and all the way up to tens of meters, hundreds of meters, depending upon how much core you actually take. When you do measurements on them in the lab, they are very well established processes to measure permeability, porosity, composition, grain size. There's a few assumptions that go in there, building these things, but it's very, very small. And so you get really good data from there. So you have really low uncertainty of your data sets when you're directly measuring rock and when you're directly measuring the fluids, because the fluids also help out through there as well. So you're actually taking a sample of the water, you're taking a sample of the hydrocarbons. You can do direct measurements on these, and you can get very good information from there. Pretty much after that, everything else is secondary. You are making a lot of assumptions. You are making a lot of data. They're very reasonable assumptions to be made, right? But the uncertainty around those data sets are now widely varying. And that includes, gravity magnetics, very low resolution, can be very powerful if that's what you need. Like figuring out basements, figuring out the transition zone going from continental to oceanic crust, lots of different things. They can be useful, but they are indirect measurements. And that includes well logs, that includes seismic, that also can include analogs. That does include analogs because it is not a direct measurement of the rocks and area that you are working on, but they are like it. So you have to take some uncertainty associated with that and recognize that it is not, I'm not measuring it from where I'm looking at, but it is a reasonable assumption to make these things. So you need to use these things because sometimes that's all we got. And particularly in areas of exploration, that will be all we have. And so we need to use those judiciously. We need to use those in the appropriate fashion and remember there's a lot of uncertainty associated with that and bring that uncertainty along with all of us when we go and talk about it and figure out the story that's happening. So along with that, we need to understand the ranges and the resolution of these data sets. All right. And so here's just a chart I put together. And you can see we have lots of different geological elements at the top, at the bottom, the different ranges that they can be in the terms of like spatial dimensions, but then also the resolution of them. So seismic is on the kilometer scale, right? We are way up there. We can get lots of good regional image, reasonable interpretation, reasonable data from there. And but it only goes down to like maybe meter scale, and typically tens of meters of scale, right? So we have to remember that you are putting a lot of geology and a lot of stratigraphy and sedimentology in particular into your resolution of your seismic data. And so then the seismic data resolution can go anywhere from 20 meters up to 100 meters. 100 meters is a really big thickness to stick a lot of information in there when you're trying to tease out a lot of these subtle stratigraphic and the sedimentological variations going on through there. And then you get down to the whole rock and the whole and other things where you actually can get log data without going down with some of the new things with FMI and other things like that. You can actually get down to centimeter scale and and into the world of more individual beds and some things like that. So remembering where your data is coming from and what data you're evaluating, that also will help you figure out how to use the attributes that you are creating and which ones are useful for to answer the resolution and the scale of the questions that you're asking yourself. So just another reminder is that, we always have to remember that as geoscientists, and particularly for Sedstrat guys and for structure guys, this is all going to go into a model. You got to build your geological model. We're always testing these things. That's another great thing that the computing power has given us nowadays, is that we can run a lot of modeling. We can run a lot of tests. We can do a lot of volumetrics. We can do a lot of dynamic testing of these data sets now, building these geological models. We also have to remember that those engineers are going to scale everything up. So we got to figure out what's important through there and what to retain and what to keep. So we are going from, microscopic scale, and they're going up to, megascopic scale. They're not making their, vertical resolution down at the bed scale that we are investigating as Strat people. They are going to be upscaling it to 5, 10 meters, whatever it takes, depending upon the cell size that they need. So we're running across a lot of different scales, a lot of different ranges, and we have to remember what are the most important parts and how can we group these things together? How can we put all this together so that eventually we can make the decisions from this, because that's all the input is going from there, is trying to make these good decisions, what's going on that. So we need to understand how our data is going to be used as well. So this is a geologic talk, so we got to throw in a few rocks. So this is from South Africa down the Karoo Basin. And you can see, seismic scale on the left. You got some nice pictures of some basin floor flans at the bottom. And these outcrops, individual outcrops go for, up to 2-3 kilometers. The whole outcrop belt is about 40 kilometers, is very well seen. And it's a nice succession from deep water basin floor flans coming up onto the slope and into the deltaic. So hopefully some of you have actually managed to get out there and look at those rocks. It's a very good area to look and see on both the seismic scale and on a well log scale of where you are in the system. There's not a lot of structure and tectonics moving around, so you can figure out and bring all these scales together from seismic scale, and then you can get up there and start touching and feeling the rocks, which is what we always need. See what those subtle grain size variations, see the stacking patterns, and seeing what well logs and what kind of core analogs that you can use from here to see how that can maybe possibly apply to your system through there. So we have to remember that as we approach and as we're doing this workflow and trying to figure out what attributes are needed, is that for seismic data, almost everything we're going to do for your stratigraphic investigation is all horizon based. So tell my students at Rice University and when I'm helping out other geoscientists, is like, you're going to be spending 70-80% of your time, if you're doing seismic interpretation, on making the best surface that you possibly can, because we're trying to get back to paleo time. We're trying to get back to that depositional system and see how that depositional system is working on a time surface. Seismic doesn't always relate to time surface for the reflectors, but generally it does, and we can get away with it, right? And so it works out pretty well when we're mapping out reflectors. And you do that on lots of different ways. And there's classes out there, and there's ways to teach it. So we're not going to go through that through here. But the more time you spend on your building your surface and making the surface as best as possible and having multiple iterations. And now there are software out there that can give you thousands of surfaces through a seismic data set based upon different criteria. Still got to figure out which ones are good, right? So it's not can't just rely on the software to pick them for you. As a geoscientist, we still need to make a good consideration and figure out which surfaces are the useful ones as we go through there. Same thing with well data. A lot more getting higher and higher resolution on the well data, but our well log responses, we're basically looking at vertical patterns, looking at finding upwards, coarsening upwards, thickening upwards, finding up, thinning upwards. And so there's lots of different patterns. So we're always looking for patterns in stratigraphy going through there. And that's what our well logs are doing. There's also some, some values where you can get porosity logs, but we're looking for the changes of that because we want to see how things are working so we can all relate it back to processes. So when we talk about processes, this is the next slide. So yeah. So we'll get to there. These, in my opinion, are the basic attributes that we need to consider. And so we don't, so in the modern day world, when we're looking at software patterns, we don't talk about thickness and continuity. Those aren't the, we talk about sweetness and all these, all these other attribute extractions that we can do. But thickness is an attribute. And I think it's a very important one. And it's a very underrated and overlooked one. But sometimes that's all we got. Right. And continuity. And this is both for continuity of the reflectors and continuity of our layers that we can interpret from our well logs. And so when we put those into context, when we figure out what those are doing across an area, this is what's going to give us the parameters to understand all these other attributes that can be very useful that we are creating, but we have to put all those attributes because if they can come out, and I've seen, unfortunately, some attributes being abused where it's just, a blob on a map. Reasonable to have when we're doing that and not just taking it and saying what it is. It still needs to be a reason because everything in our data sets is related to the geology of the earth. When you get into the well, it's those stacking patterns, the sand and the clay percentages. That's the basics is what we're having is what's the grain size doing and how is that being distributed through time. And then also for seismic is I think there needs to getting a bit more into it, but we're not going to go show examples of this today, but because sedimentology changes typically on a resolution below seismic, there are subtle variations in individual reflectors that can be used to, in conjunction with lots of other things, can be used to figure out what's happening. All right. So if we're looking at why we get these attributes, and that is the basics of you have to understand sedimentology, right? When you're doing sedimentology and stratigraphic analysis, you need to understand what world you're in. Right? Are you on a coastal setting? Are you in an offshore setting? Are you in a fluvial setting? And these are the first order controls that I think about when I'm thinking about investigation. As I want to know what I'm looking at. I want to know where my sediments are coming from. How far away is it? How mature are the sediments? How close are my mountains? Right? Am I, what composition is it? Because that's is it more carbonate class or is it siliciclastic class? How much feldspars should be in my system? Those all affect my data. All right. So I can interpret them appropriately. So I can understand all these things. So I need to know how much is coming out there. Am I sediment starved? Do I have lots of sediment supply? Those will all influence my interpretation. Same thing with energy of the system. What is when I say energy is what is the mechanism that is moving the class? Am I in wave dominated system, fluvial? Am I all gravity, flow, turbidite systems, mass transport complexes? Am I aeolian? Am I getting all wind? These will help me determine the three-dimensional aspects of my deposition, which will then help me determine my three-dimensional aspects of my porosity and permeability trends, which is what we're ultimately trying to get to. And then all those are being influenced by your topography. All right. So I want to know where my highs are. I want to know where my lows are. I want to know how this energy is being diverted by my topography. So understanding that as well can start bringing in the buckets of what I need to be thinking about. Because if I know I'm in a coastal environment, I probably don't need to be thinking about submarine fan systems and turbidites because I got other things happening through there. I don't need to be thinking about desert systems, right? Because I got other energy going on through there. So I can start thinking about how these processes distribute my sands. That way I can better interpret the attributes that I can get from my data sets. So let's look at a data set. I found this online. This is from the TGS website, and this is from I'm, I'm sorry, Wele. I'm assuming is that's close enough. Oh, thank you very much. I actually feel pretty good now. All right, the Wele 3D fast track. This is 3D fast track for the PSTM. This is the really large um, uh, shoot that TGS is going on to now. This is their show line that they have up on their website and out in this deep water setting. So I think, well, what's more fun than try to find the newest data set, and let's go see what we can see. So if we look at this basins through here, so we'll go to the next slide, and you can see, okay, we got some interesting things happening through there. As much as it chagrins me to say and pains me to say, as a sedimentologist, we still need to interpret our faults first. Right? We still need to understand what the faulting is because we want to know where our stratigraphy is going away based upon depositional processes, not structure. So we have to map out all our faults. We have to understand where our reflectors are going and where they're stopping, and we need to know why. If it's faulting, then we got to map all these faults so we can ignore them. Is what it comes down to as a sedimentologist. So, all right. So just a couple of surfaces that you go through here. Mapping out through there, and that's just based upon those criteria that we said before, finding out because we're basically with stratigraphy and seismic data, you just try to map packages. You're just trying to figure out packages that are related in some way together, so that we can say, okay, mostly what's happening in this package is all the same, and then something changed and something goes on through there. So looking at reflector terminations, seismic stratigraphy, all those sorts of things that hope that you've been taught through the years and have refined your skill sets. So we're going to look at this one particular section through here in this basin through there, right? And so this is where it gets into thickness and continuity, just these basic things. So that's what I really like about these attributes, is because I don't need a 3D data set. I just need a 2D line, and I can really start figuring out what buckets there are. And now I can go from here into 3D data set if I want to, or if this is all I got, I still have a reasonable starting to build a reasonable geological story that hopefully I could build up to defend my interpretation going on through there. So when you look at this data set, you got some faulting in the middle, right? You got some more continuous on the right-hand basin, right? Go back. So more continuous on the right-hand basin going on through there, and maybe a bit more discontinuous reflectors going on the second-hand on the left-hand basin, right? And then going up onto the anticline, going on to there. Is that continuous? Is that discontinuous? I'm not too sure. So, but we're going to come into this basin through here, because go back to, and we'll see through there. So, but also, go back one more, please. Thank you. You can see that we have some thickness variations through here as well, right? So we got some continuity variations through here, and we have some thickness where the dots are. That section is thicker than going off to the sides. Now, as a sedimentologist, I'm very comfortable with qualitative statements like that, because that still can help me figure out where I put my quantitative data sets, right? But here it's interesting because I got two kind of thickness basin centers in this interval. So that's telling me that maybe that central fault system through there might have been active. There's something was going on through there, making two individual basins that up above maybe coalesce and become one basin. So now I'm already starting to help me with my structural story as well, my story through time, what's happening through here, just by knowing that I have a thickness in two sections through there. So I have two separate lows. That's where my topography comes in. I also noticed is that, there's some onlaps on both sides. There's some onlaps in that left-hand basin. There's some onlaps onto that high. So that's also more indications that I have a structural high in the middle of these basins, at least in the lower portion of the section that we're looking at through here. And then maybe it comes together through there, because this is a pretty big section. This is hundreds of meters, right? So we got to go from big into little and try to understand those things. Well, go back, not done yet. Still more stuff to do here. There's still lots more things to go over. So now we're looking at the discontinuous to the continuous things. Whatever is going on in that left-hand basin, it's different in the right-hand basin. And so now we go, okay, well, now I have to come up with a different process. I got to think something is happening here that is different from one basin to the next. Sands and distributing my sediments, right? Now I know that I'm in a deep water setting. I go to my models, I go to my analogs, I go to my things, and it's like, where do I find where could I get set up discontinuous reflectors? Well, if I have a discontinuous reflector, that means that things are changing quickly, right? If I have continuous reflectors, that means things are changing slowly. So if I have discontinuous reflectors, then I have to be looking up more at the more proximal setting, maybe on the slope or my proximal basin floor plan, where I'm getting a lot more channelization and other things, where I go from one side from the left side of that model to the right side of the model, things are changing. If I go out into the true distributary complex of a submarine fan system, things are changing more slowly. So I should set up more continuous reflectors. So already just from here, I'm looking at different elements of the same depositional environment. I'm still in a deep water setting. I'm in a basin floor. I'm in a basin. I'm on the basin floor. But at one point, I'm closer to maybe that slope, and I'm closer to more of a channelization setting. And the other one, I'm farther away, and I'm out more in that distributary system. So just from my thickness and from my continuity, I'm already figuring out and getting into the details of what I should be expecting to see when I do some more finer scale and these higher end attribute work going on through there. Now I got to figure out, is that reasonable? Why does that happen? Part of that's a structural story. Part of that is I got discontinuous should I expect to see discontinuous stuff in the basin center? And then when I go up to the left-hand side and I see it's not quite continuous, but it's not semi-continuous, because eventually that's where we want to go anyway, because we're going to find hydrocarbons. It's probably going to be in the structural high. So what I'm really trying to figure out is, if I can figure out what's going on where I have some good data, then I can bring it up into my real area of investigation is. So let's go over there. Let's go over and look at this. So we got a pretty big thick section through here. So now I got to figure out, okay, it's thinning from the basin center up onto the high, but is everything thinning? And so now I got to pull this apart and figure out what sections are thinning. So added a few more surfaces on here that hopefully everybody can see. And again, looking at some more reflector terminations, because if I have a reflector termination that's onlapping, I have to have topography. I have to have a high that it is onlapping onto. So that's telling me something about its thinning. That section is going from the basin up onto the high. That's thinning. That's telling me that I have a structural high up there. If I have a structural high, my process sedimentology is telling me that turbidites don't like going up on highs, or if it does go up on a high, it's just the top of the cloud. It's just the finest grain portion, and non-reservoir grade material is going on up through there. But it's not everything is going on up through there. There are a couple of places in between the green and the blue that I don't find my reflected terminations. And so again, the getting now down into that, getting closer to that resolution that we need in those stacking patterns, and trying to figure out in my actual reservoir, because this is, even one of these reflectors could be a full reservoir that could be very economic and prolific. I'll need to understand what's happening in between all these guys. As we look into what is thinning through there, you can now see that it's more discontinuous in those areas that are thinning. I think the next one. Yeah, so we got some different basin centers going on through there, some different even thickness patterns happening at this scale going on through there. And they've got some more continuous at the bottom, and then it gets more discontinuous in those other basin centers. So again, now I'm getting at that higher resolution, still the same attributes, but now I'm getting even more details in how I'm tearing apart this particular basin through there. Now let's look at the discontinuities themselves. So if you go to the next one, you can actually see that I got a bunch of smiley faces through there. I got a bunch of little, dishes going on through there that happens to be in my discontinuous stuff. And if I really started mapping all these things out, is it reasonable to find those things? Yes, because we are in a more of the discontinuous setting. We're in a deep water channel. We're a deep water submarine fan system going on through here. I should be expecting channelization going on through here. And then you can actually start pulling out individual reflectors and finding out, hey, I got a bunch of different channels through here. I even got a little bit of migration through there on the channel on the very to the right happening through there. I don't have this all the time. I have this coming and going. So now I'm even getting higher resolution scale of when my submarine fan systems are being developed through here, where I have lots of channelization, and then I have a little bit of in the blue section, and then I have a little bit of quiescence, a little bit, but then it really picks up again and even scours down even more in the green section. So now I'm thinking that relating it back to sediment supply into this area. So what happened is there's something up on the Nigeria slope that moves some channels into this area. Could be some delta switching, and I can relate all that back to my my regional setting just from looking at this one seismic line going on through there. Now taking it up into the on the anticline there, that's getting a little bit more fuzzy and a little things, some things, and there might be, you know, it may be in that section between the green and the blue. Yeah, it gets a little bit discontinuous up through there, and maybe some different amplitude variation. And so this is where mapping out those surfaces, taking the time to do that, getting some more attributes through there. Maybe at this time there was the deposition through here buried that high, and I can actually get channels and other submarine fan systems on top of my high that was later uplifted. So I can't put reservoir grade material onto here. So just looking at continuity and thickness on a 2D seismic line from the internet, from the show line from TGS, we actually got a pretty good idea of what to be expecting and what to be looking for in this area. And that's just based upon some very, limited data sets, just these a couple of attributes. But now we have those parameters. Now we have that starting that geological model that you can stick all these other uncertain and maybe a bit more ambiguous attributes that you can pull out from here to understand what they mean and where they can go. So these types of attributes, these basic attributes, can really help you sort out what to be looking for and how to interpret those more complex attributes going on through there. So this was a seismic characterization. We go to the next one. This is looking at wells. You can do the same things with wells, because this is actually onshore Louisiana, and this is more of a coastal environment going on through here, because if I could figure one that had wells on it. And you can see that where the prospect is, right? Now here, I tried my best mapping this sucker, but I don't trust any of it, right? Because that seismic data is bad, right? It's just we reprocess this. We've tried to get this going as well as, but even, looking at this in lots of different ways, I'm not sure exactly even my mapping, even my basic mapping, and I'm not going to trust any attributes going on through there. I have one well in there that had some hydrocarbons in it, and we just don't know where to go from there. But we do have other wells in that same basin, but are higher. So I got to use what I got to use, right? This is all I have to work for. So let's see how I can use these well data sets. And again, this is just looking at thickness and continuity to try to figure out what the possibilities are for this data set through here. So go to the next slide, and you can see that, okay, let's break this out. Looking at some things, I got some faults happening through here. I got my basic, other working on where we're looking at my prospect, and I'm just trying to figure out, I know I'm going up dip from there somewhere, but how far can I take these sands? How far can I take this potential reservoir into this area going on through there? I have all these wells. I did some correlations through there. Go to the next slide. So I look back at this area. I know what time I'm in. I know how old this is. I go and look at some regional work, and I know that I should be expecting to see I'm in a fluvial dominated delta system. All right. So now I'm already starting to think, hey, fluvial dominated delta system on a coast. I should be expecting to find overbank things. I should be expecting to find some channel systems. I'm in between two wave dominated systems. So even though this has been designated as a fluvial dominated delta system, I still got a lot of wave action going on through here, right? So I'm going to be, even though it's fluvial dominated, it'd be wave influence. There's going to be all sorts of things. So I'm already thinking processes. I'm already thinking, what should I be expecting to see in my very low, I can't get much from seismic, and I only got, like 3 well logs to work with, right? But I should be thinking about how would my sands be distributed in this type of environment. So I bring along a model. Go to the next one. So I have a model that's go back out in the literature. It's good work out through there. And I just think, what should I be expecting to see in 3 dimensions? And so I should be expecting to see all the, river coming out, the delta building, but my waves are going to be, sifting through and pushing my sands along, and I should be expecting some beach ridges, some dunes. That's pretty good. I like that. That's going to distribute my reservoir along through this area. So I have this model now in my head. All right. I go back to my wells, and now I start interpreting those stacking patterns. Basically, where is my sand, and my mud ratio as it goes up through time. And I'm finding out that I got, this coarsening and thickening upwards in a whole bunch of these. This is just from one well, a whole bunch of these stacked patterns of these finding upwards, thickening upwards, the green arrows, the thickening upwards and coarsening upwards, topped by something that's thinning and finding upwards. So a whole series of these things. And I know from lots of different analogs, lots of different processes, lots of different papers, this is classic beach, classic shore face kind of expectation of what you have and the deposits when you're going through there. Lots of little variations, and you can start getting into, overall you have that pattern, but you also have smaller little patterns of coarsening and thickening upwards, tapped with finding upwards. So now you can really start getting in, even from this old SP logs. These are all from the 50s and 60s. Even from these old logs, I can still get a lot of ideas of these patterns and assign them some processes. So I can actually start looking at smaller sea level variations and smaller, finer resolution of what's happening through there and the distribution of my sands. So I got this pattern going from this one well. I take that out to the next slide. I take that out to my other wells at the same interval that overall package. I have them correlated across from well 2 to well 1 to well 3. And I see that, hey, lo and behold, I see this pattern overall, as well as I can maybe even correlate some of these smaller patterns, some of these thinner patterns through there, some of the higher resolution patterns going on through there. So it gives me a good feeling that I could take this pattern across my full area of investigation of where I think my prospect is. I should be able to distribute these sands, go from there. There's going to be some variation. There's going to be lots of higher scale facies variations going on through here, but at least this package should distribute through there. And hey, it matches what my process sedimentology and my environment is telling me. So I'm getting all my evidence lined up, and it's all telling me the same story. I go from there, and I was like, okay, well, now let me start mapping out the thicknesses. And so now I actually do numbers. I actually say, how is it really thickening? This is what I'm hoping it is. Let's do some numbers. And this is just basic, figuring out between my surfaces, as well as in the sand packages themselves, as well as the muds in between. And they're pretty much, within just a few percentages of one another. These packages are very consistent across this area. Again, that matches what my depositional model and my processes should be telling me. I go through there. I have a little bit, maybe some sand layering, thinning in G, and I have this 300-foot layer in well 3 at the bottom. Well, that doesn't match anything else I have, but I'm in a fluvial dominated system. I should be expecting channels. Well, that's a very reasonable interpretation that, hey, that well just happened to hit a channel through there. So it's not outside of my story, outside of what I should be expecting to see in this area going through there. Now, the question comes in as well, is that I don't have any data from my alpha and beta sands. I only have one well, but I have all the subsequent wells sitting on top of it that say this environment hasn't changed that much. I'm getting nice correlation and nice distribution of my sands across my entire prospect area in the stratigraphy above my target zone. It's reasonable to expect that it's below my target zone as well, that not much has changed. I don't think much has changed. So you bring that into there. Go to the next slide and you say, okay, well, let's look at modern day analogs. Will this match what I'm expecting to see in this environment to distribute along through there so I can bring it down into my target zone? Well, you just, pick and choose what it is. Up here, I picked the Danube Delta, and you can see that my prospect outline fits along some really nice, delta plains and sand ridges. And so I am on the right scale. So now I'm getting back to scale and resolution. Is it reasonable to expect all those sands to be hooking up together on the same scale? Yes, I have it in the modern day world. And so it works out very well that is not an unreasonable expectation that all those sands should be connected and that my target sand will be distributed over the same area. Go back in there and then just go back in the literature and I was getting, no, you can go on the next one. You got the same log motifs going on through there. So everything matches. And so you're building a nice story, pretty robust story with some very limited data sets. But you're building a nice story that everything fits together going on through there just from thickness and continuity. And then with the wells here with the stacking patterns, trying to sort out through that. And so, yeah, so going through there, so it's highly probable that all the sands, because these sands match through here very nicely, you're going to be able to say, hey, my environment is not changed that much from down below. There will be some subtle variations, but it's reasonable to expect that these sands will be distributed throughout the entire way. So just using these basic attributes, thickness and continuity, and then a little bit of stacking patterns when you have the wells, of just what's happening. You can bring it in around process sedimentology. You can bring it around your regional setting and looking at your data sets and come up with a pretty robust geological model that if you can get some more attributes in there, you can sort through that and find out and place all those really higher resolution attributes and all this fancy stuff that's coming out today into a proper context so that you can understand that. Then just going along through there, get some, this is more some fun images and some nice things to look at. There are some other things you can do that I've done in the past, particularly for seismic volumes. I like looking at 3 dimensions, and this is not doing any extractions, not doing anything. It's just selectively viewing portions of your seismic volume. And typically this would begin on horizon base. So you do a horizon-based sub-volume, and you just selectively turn off. You just make transparent. You just use the opacity curve and just bring out the surface, the amplitudes that you're interested in. And then I have found spectral decomposition is just awesome and really great at sifting through and finding some of these really higher resolution types of things going on through there. Again, horizon-based for both these guys because you want to get back to paleo time. So I guess a couple of images going through there. So here's just some maximum amplitude, looking at a big, 50, 100 millisecond section. You're looking at, some potential prospects, and you are seeing some trends and some different things there. Again, this is in a deep water setting. Go to the next one, looking at an RMS amplitude based upon maybe it's a little bit different window. Color bars are very important. I can't stress color bars are very important to try to figure out and how to highlight the parts that you want. And now you can start seeing lots of channels, running across this area. When you look at just looking at volume visualization and just doing opacity, go to the next one. You can start getting your proper window of investigation going on through here. Now we can start building the story even. So this is at the bottom of the system, early stages. You can see in the center some nice channel going through that one prospect with lots of reds on the outside. The channels don't have anything in them, but all the sands are now being deposited outside. Same thing on the left-hand channel system going through there. Lots of overbank, but you know exactly where the overbank sands are going. When these turbidites are coming down and where the clouds are being deposited, you can actually start mimicking, saying this is where I go from sands to silts to muds. When you keep now, but you're on a 20 millisecond window, and as you go up this 20 milliseconds, you go to the next one, you can see how these systems are turning off and going away. You have another system that's being built up now, even more on the right-hand side, while that central system is shutting down. And as you go to the next slide, at the end of the system, you're seeing that middle system is now gone and something else has taken over. And then on the left-hand system, you can see that in the channel, the yellows and things are in there. Now all the sands that used to be going over, the turbidites were large enough that were going over the sides and not depositing anything internal, are now staying in the channel systems themselves. And that's what's filling the channel as this system is going away and dying out. So looking at these and getting the right proper interval of investigation, you can really start ripping apart the life of this system as well and go looking at the processes going on through there. Then what's fun is this is what spectral decomposition can get it when you combine in RGB blending, the different frequency volumes. So now you're getting into the frequency domain with a little bit of amplitude throwing into there. And you combine these things where here the hotter colors, the reds and the yellows are the thickers, the blues and the greens are the thinner sections. And so you can substitute this for sand, relating it back to processes and sedimentology. You can relate it back to where my sands are and where my muds and other sections are going on through there. So this really pops it out. And this is actually really good for faulting. You can see some nice faulting. And it also actually brings out some DHIs on this one as well. On that left hand where you see all those fault patterns. Below the nice bend in that channel, you can actually see an exaggerated reds and yellows in between some faults. And so that's a little fault bounded little gas accumulation going on through there. So this actually helps out with DHIs as well. So this is just some examples of some different ways to do it. And these workflows, especially with spectral decomposition, is easier and easier to do all the time with the software patterns to go up through there. And to really get some of that subtle details that we need to investigate how our sands and how our reservoir is being distributed out, so we can really make a good prediction of that permeability porosity variation going into there. So it's for volumetrics, for everything that stems off from there. So I would like just to encourage everyone to start off with thickness and continuity and just think about those, and that really helps you figure out what to do next and where it goes on from that section through there. So I hope this wasn't just more than they got something out of this, and it wasn't just more than the mad ravings of a sedimentologist. But I found that these are things that I typically start off with that really help me figure out and can really focus me on the questions that I have going on from there. So this is just a movie going through that whole section because it's pretty. So we'll let this run in the background. But I'm happy to answer any questions that anybody has.
Thank you so much, Eric. I enjoyed listening to your presentation. It's very rich, and I think everybody in the room and online would agree. Another round of applause for Eric. Okay, we'll start with Q&A now, and we'll start with the room. So anyone with question in the room?
I really love the display that amazing job. Thank you. I noticed that you really concentrated on RMS. Did you put some thought into maybe also like MPA? Because they can be some indication as to the real presence of the sand compared to monkey layers. This has been some issue night and temperature. And the second question is around like on 2D. So when you don't have like 3D data, when you can really run out like the side features that have to be see. What have you done in the past? Because I've seen all that method, like okay, very useful, but I'm very curious about your approach. Thank you.
So for the attributes that I showed RMS stuff, those are just some basic things, and you could use your favorite attributes, and you need to tailor it to your data sets, your resolution of your data sets, as well as your vintages of your data sets, because some of some of these older 3D data sets, if they're not reprocessed yet, some of these things are some of the attributes are not as useful as others. So these were just ones that I had for examples as well for the RMS. I like RMS because it does have a thickness component to it. However, you're kind of taking that out a little bit because you are saying what your window is. RMSs really work well when it goes between two surfaces because it adds that thickness component to it. But when I'm starting out in this type of investigation where I'm looking at thickness and continuity, just looking at these basic attributes and just your absolute just your highest minimum, your highest maximum attributes, these simple attribute extractions help me guide what I'm going to do next, instead of just we're always constantly just doing what we can and just, seeing what comes out of it. But those things can really help me figure out, am I seeing what I expect to be seeing in my distribution of my sediments as we go through there? So that was just one of many attributes that you could use. For when all you got is 2D data sets and minimal 2D data sets, this is where, your thickness maps and other things like that can really start helping out. Because I've seen people, and I've probably done it myself, try to do attribute extractions and things on 2D data sets. And it, depending upon if they're closely spaced 2D lines, you can get a little bit out of it and maybe get a little bit of insight into it. I don't know if I would show too much of that, and based on, but if that's what you have, based upon, because sometimes, particularly when you have channel systems where you got some really big contrasts in your reflection coefficients from inside a channel to outside a channel, where things happen quickly, and if your lines are spaced close enough, then you can kind of map out some channel features and some other things that happen through there on 2D based attribute extractions. But it is limited. When you get internal to things through there, then you have to start looking at trying to understand, because of 2D lines, you're bringing in a lot of three-dimensional effects onto your 2D lines. So you got to try to remember what's happening on your line itself, and not that seismic is being affected by the things that are outside of it. And again, that's where it has come into, does it look more continuous or more discontinuous? And so looking at some of the basic patterns, because your resolution is so low, your uncertainty is going to be much higher. So that's where it comes into knowing what my data is, what my resolution of my data is, where it can get it, so I can know how to bring that uncertainty along in my interpretational model. And to know how much, I mean, you can always go, and I always like to push past my resolution so that I know where it is. But then you have to remember to come back and say, no, I can do these things. I can make these surfaces in this really poor 2D seismic lines, but I don't even trust it. I don't even think it's there. I think I'm pushing the envelope too far. And so I'm going to come back to where I feel more comfortable as an interpreter and where I can defend my geological model.
Thank you, Erik, for answer to that question. So let's go to Slido. Oh, there's another question. Let's go around the different platform. I'll come back to the room, okay? All right, so let's go to Slido. We see one question voted up on Slido, and I'll read it. It says, based on the inherent uncertainties in the geologic data that goes into geologic models, would you advise we make scenario modeling a best practice for models?
Most definitely, yes. Because of the inherent uncertainty of the data sets, then we need scenario modeling, and but the scenarios themselves will be based upon the resolution of your data set. So modern day 3Ds, we got some pretty good, you can get down to some pretty high resolution, and where you're at overall in the basin setting, where you're in that distributary complex of a submarine fan system, whether you're on the slope, whether you're inside the channel, outside the channel. And so your scenarios will then be different than if you're not even too sure, where am I on the coast? Am I in a tidally dominated system or a wave dominated system, and just mapping through, do I go high or do I go low? And so you make some assumptions in these different scenarios and you stick with it. You go and say, for this interpretation, I'm going to make the assumption that I'm in a wave dominated system, or I'm going to make the assumption that whenever I take this reflector across, I'm always going to go high, or whatever it is, recognizing that there's some uncertainty in that assumption. But if you go down, then you go to the end and then say, hey, does this now make geologically reasonable sense? The dimensions that I have, the thickness, the continuity, all these other attributes that you could put together, does that make actual geologic sense with the way process sedimentology works? Should I be expecting my deposits, my sands, to be deposited in this configuration or not? And if it's hard to say yes, then maybe that's not a good scenario.
I totally agree with you, Erik. Even for economic decision making, whether you go FID on some project, you need scenarios, right?
Yes, very much so.
Yeah. So let's do another question on Slido before we move to the chat online on Zoom, and give those people a chance as well. So with the advent of new technologies, is there a need to go back and review some of the legacy geologic models?
Well, the need will be dependent upon, well, basically whether your boss says to or not. And that's based upon economic decisions. So, but I would always say that when you are coming back into an area for exploration, the work that was done before was done for a reason. And so you need to understand why that was done, what decisions were made, what data they had to work with to make those decisions and to build that geological model. Then when you have new information, you have to incorporate that in. And that goes along just the life of a project itself. When you go from exploration into discovery, appraisal, development, you're constantly getting new information. And so you should be refining all the geological models anyway to make sure you understand what's there. So every time you get new information, you should be tweaking your model going on through there. And then also, particularly for these older models, and what your question is that if you haven't revisited that area for a little while, you need to go back out into the literature, back out into our overall geological understanding of what's happening in that, because we are now getting better and better ideas of how sands and muds are being distributed around the world, how salt tectonic works, how thrust systems are moving on so we can make better fault interpretation, particularly in areas where we don't have a lot. The seismic is not quite so good, particularly when you got thrust systems and all sorts of stuff. Looking underneath those things, you see a lot of variation through that. So when I say new information, it could be at your area itself, or it could just be new geologic processes and ideas of how these systems overall work. So that can be influence rebuilding the geologic model as well.
Thank you very much. I'm going to take that so I can see the screen. We're going on Zoom chat now so that we can give the people on the chat a chance to ask questions. So the first question is, Erik kept mentioning attributes. Are the attributes the same as geological methods, and what are in situ patterns?
So attributes is a little bit of a catch-all type of word as well. So I use the term attributes in more of the actual characteristic, a measurable characteristic of some data set. So every data set has an attribute. And so then those attributes you need to relate to the geology some ways. When I think of geological methods, I think more of workflows and processes in order to get to those attributes going on through there. So some geological methods and working through these processes you incorporate attributes and you incorporate sort of things. So that's just a little bit of wording going on through there. So.
Thank you so much. I'm going to take another question on the chat. Julius thanks you for great presentation and for sharing a simplified approach on seismic data evaluation analysis. And then he has a question, and it's, would you recommend if the available seismic data does not reveal any visible geological features from the basic seismic attributes to define reservoir geometry in the appraisal development stage?
So I would say that every data set from the subsurface can provide geological information. The question is how good is it? What's the resolution? And in the end, do you believe it? And can you defend it? That's the question. But every data set is always going to give you something. If I don't see anything on my seismic at a certain depth, that's because something is messing it up. So it's still related to geology. Now, it doesn't help me with what I'm trying to figure out at that actual depth location, but it does tell me something about the overall geology and the history of the area, right? So there's always some information that you can get from well logs, from seismic, no matter how poor it is, no matter how uncertain it is, there's always a little bit of information that you can get from there. And then you just need to go and find another data set, because there's always another data set, to go and look and say, hey, is my initial interpretation, is my initial geological model, my first thoughts here, can I get a similar story? Can I match that to another data set? Can I confirm that with another data set? Is it all pushing me towards the same story or not? Or if I'm getting a different type of story where I now have to go back to my poor data set, very highly uncertain data set, and reinterpret it in a different way. So there's always something that can be done. In the end, it's what uncertainty is associated with that, and is that good enough? The interpretation that you come up with, is that good enough to make whatever decision that you need to make? Or do you need to go collect more data? That's what it comes down to.
All right. The next question on the Zoom chat is, first of all, thank you, Scott, for nice presentation. And then the question is, what are your major considerations for well planning in a deep water setting? And then two, within the various deep water settings, how can you differentiate sand quality and reservoir architectures?
So for well planning, that is going to be the geologist in conjunction with the drilling engineers and all the operations guys. And that should be along with the full well bore. So don't forget the upper stuff, because as you're drilling along, particularly in these expensive deep water wells, you need to make sure that you have a prediction of everything that you go through. And so all these techniques that we're doing for the actual target zone where we think there's hydrocarbons, you can apply them to the shallow part as well, because we want to know, the drillers want to know where the problems are going to be. The drillers want to know where the mudstone is, so they know where to set casing and all those sorts of things. And so if you can push your casing string down another 1,000 feet, that's some money saved. So these all that aspects goes in there. So your sedimentological, your stratigraphic interpretation is important for your well planning succession. And then also goes into some more details in your completions technologies and all sorts of things going on through there. So every stage, in my opinion, of course, I'm a sedimentologist, so I think so. There's some elements of the work there of what is in the ground, what your sediments are doing, and how that affects what's going to happen with your well bore and everything that goes into the well bore itself. What was the second part?
Okay,
Oh,
in the various waters, how can you sand quality?
so from seismic data sets, trying to figure out sand quality and reservoir quality in general, going on through there. You're looking at secondary data sets. So it's lots of assumptions, there's lots of inferences, there's some uncertainty going on through there. And this is where absolutes get a little fuzzy, but you can definitely do qualitative things. So when you are close to your axis of your deep water fan system, you know you have higher energy, which means you can move bigger class. Bigger class generally give you greater porosity and permeability. So you can use your process sedimentology, you can use your relationships of that system that you're interpreting through there to say, hey, this area at least will probably have a higher quality of reservoir than when I get farther away, where my energy lowers and I can't move as big as class. So that is a very qualitative type of things, but that's what you build into your reservoir model, into your geological model to do your dynamic testing and do your volumetric calculations. You just say this area over here should be better reservoir quality than this area over there. The absolutes that go into there, that's where, again, you have to take in your analogs, what field is going next door, any other rock data that you have, looking at outcrops and seeing what those relationships are, what your starting points are. But if you know the relationships in your area, that at least this reservoir quality should be better than that reservoir quality, that's a starting point to at least put the relationships correct. And then you can play around with scenarios and sensitivities of how good is it and how bad can it be.
Thank you, Scott. We'll come back to the room now and take questions. Anyone?
Thank you very much, Scott. Very exciting presentation. So contorites are interesting plays being chased around down offshore Brazil, Santos, Campos Basin, Namibia. It's often quite challenging to differentiate on seismic between contorites and turbidites. Could you give pointers, with respect to attributes that could help us, actually differentiate contorites from turbidites on seismic?
Sure. Well, it gets back to energy, right? Turbidity systems, they are gravity flow, they are going downhill. So the energy is internal turbulence, right? And they are going to go into the lows. They are going downhill. Contour systems are ocean currents, and they are going to be going parallel to your slope, right? So you already have a difference right there, almost a 90-degree difference between the orientation of your deposits. So turbidity systems, you're mostly going, and this is a very general sense, but you're going into the basin, whereas contours are going to be going along the basin. The other thing is that contour currents happen over a longer bit of time. Turbidity currents are very short, but big contour currents is limited. This is where your sediment supply comes in. So turbidite systems can have much greater sediments and so build up a lot of things. Whereas contourites are just taking what was already in there. So you get a lot of contourite modified turbidite systems. So you're smearing out your submarine fan systems, you're smearing these things out. When you go look at the examples, and if you just look at the literature for contourites, they have some nice drifts. They call them they go into the drift systems, and they can very well seen on some shallow seismics. Some nice examples. Hess just drilled up a system off the coast of Newfoundland, and I think they wrote a paper on it. Pretty sure they wrote a paper on it. I think Rick Bobuff and Roy Fitzsimmons have done some papers on that. And so you can see, so there's a lot more good work being done on how contourite systems are smearing out and modifying these turbidite systems through there. Now we have to remember that contourites, the energy is much lower, and so you can't move as big of a class. So they can modify your turbidite systems, but so far they haven't proven to be really good, robust reservoir systems as well, because they can only move they can move up to medium sand and maybe some coarse sand, but not much more than that from what I've seen. So the orientation is going to be a little bit different. The piles of sand that a contourite makes is more of a one-sided kind of drift on the side. You have to understand your ocean currents. There's always associated with some sort of topography going on from there to know whether it's expected or not, which is very different from turbidite systems in the distribution of your attributes. You're not going to get as big of a reflection coefficient off of contourites as you would off of sand, because the sand is going to be cleaner. And so your velocity and density differences between the overlying muds are going to be more stark. And so your attributes, the actual reflection coefficients, so your amplitudes and things are going to be a little different as well. So there's enough. It's subtle, but there's enough to really sift through it and understand whether or not you have a contourite influence in your deep water setting. Is that too much or too little?
Yeah, I mean, contourites have been in the technical research discussions lately, and I have a lot of questions. I will talk to you about it offline. All right, there's another question in the room.
Thank you, Professor Erik. I know you said I should call you Erik, but sorry, I'm a Nigerian, so. Yes, those two things you've spoken about continuity and thickness, are age-long workflows that people before us have used, perhaps since the advent of well logs and seismics, or even before then. People are always looking for continuity and also looking for the thickness packages. My question is the advent of technology, particularly, is it from me? Okay. Particularly AI, from where you say, I mean, that is taking over everywhere in the industry. And from where you see some of these workflows How much of it can it be AI enhanced? Should we as geos, both the old and the young, look for opportunities to begin to pick up on some of the skill sets of how to use AI in some of these things? Because some of those workflows are being bedded into AI as we speak.
The short answer is yes, it's coming, it's here. So we need to understand these tools because it's another tool in our toolbox, right? It is not the answer, but it is an answer, and we need to evaluate what it's giving us to see if it's a good answer or not. For those of us who's been around for 30 years, we have seen, it's all AI, but fuzzy logic, machine learning, all the auto picking of horizons and faults, that has been going on for the last 50 years, right? It still hasn't taken over, was still not good enough to substitute what a geologist and geophysicist can do, right? So because of the data sets that we have, because of this inherent uncertainty in what it's doing, is you need to make a judgment call of where to take your horizon. AI can give you, like I said, thousands of surfaces, right? But it's only seeing the data that it's given. And the data has enough uncertainty, and the resolution is low enough that that surface will go high when it should be going low, even though mathematically it is correct. And so we need to, as a geoscience community, we have to bring that into the place to say, no, that is not a geologically reasonable scenario coming in through there. All this AI stuff, really good for signal processing. It can really get away through the noise. And so hopefully I won't have to complain to my geophysicist, my processing geophysicist so much to give me a better image to interpret all my geology on. So it is providing some things, and it is helping us because we are having this vast volume of information and data that's now coming at us, right? So being able to sift through that, being able to pull out the appropriate ranges to put into our models is important. There's a lot of work being done out there in building up these databases, and academics to try to look at all these examples around the world, throwing them into this database so that we can pull out, hey, I have a channel system with that has levees built on it that's this size and this dimensions and how many stories, how many other places around the world have that, and on outcrops and other fields they have rock data. I could use that. I get a more robust range and more defendable range that I could stick into my models. So it's really good through sifting through data. Still not very good at interpretation, in my opinion.
Thank you, Scott. So one last question from Slido. I think this is probably specific to a slide you showed. Is it advisable to chase the structural high channel levels within the channel complex as a prospect, especially if it shows some bright amplitude reflectors?
Both are reasonable. We know that the anticline, that structural high, that's a really good spot for a trap, right? So that's the first inclination that we do that we go through there to see what sediments and what grain size, potential grain size could be on that high, because we know that's a trapping configuration that works. We also know that stratigraphic traps work as well, particularly along West Africa, north of Nigeria, all those nice discoveries. So, but that's a three-dimensional problem. So you have to figure out chasing this system. We know we're in a very channelized system. Where are those channels coming from? It goes into a slope. Chasing that guy up the slope and seeing if those sands could potentially pinch out up the slope and have a ceiling lithology sitting on top of it. Both are very valid concepts. You just have to chase those down. But just from that 2D line, you came up with two really robust concepts to see which one will work and which one can make economic sense and which one's to chase down.
Thank you so much, Scott. Let's give Scott a round of applause. You may have your seat, please. We've come to the end of the Q&A session, and I want to thank the audience, everybody online. Questions from Slido as well as from the room. Can you switch off this? Sure what is happening. Okay, I will give it another try. So it's been an engaging session so far. Let's take a few announcements before we take sponsors' remarks. So I'm just waiting for the slides to come up and then we'll take some announcements. So while we're waiting, I'm sure you are aware of the upcoming annual NAPE International conference and exhibition. It normally comes up in the second week of November. And if you are yet to register, if you will be around the area, it's usually in Lake Nigeria. Please, this is the time to register.
End of this month.
All right. Thank you, sir, for that reminder. By the way, Professor Babalola is one of our veteran geologists in Nigeria. Thank you for coming. All right, so a few announcements. So on September 24, there will be another technical business meeting. The main one at the Eco Hotel. When I say main one, you know, we have different chapters. So this will be in Lagos. And you can see it's a very, you know, relevant topic right there. Integrated planning, breaking silos to build a profitable and resilient upstream sector. It's about the business, right? So, and of course, this is the cycle when we do elections for the upcoming new officers to take over. And this is just a slide for know your candidate. And if you do not know the details to vote, it's right there at the bottom. You go to that member portal, use your username, which is the email address at registration, and then your password will be your membership ID. And these are the candidates for president-elect, for president and UAP chairman. We see some familiar faces there. Yes, I was talking about the NAPE AICE for 2025. By the way, NAPE celebrated 50 years of NAPE earlier this year, but this is the 43rd conference. So, yeah. So, can you go back one slide? Yeah, so the theme for this year's NAPE conference is revitalizing the Nigerian petroleum exploration and production strategies for energy security and sustainable development. It's a very relevant topic, and those are the registration information at the bottom right there. And for inquiries, you can contact the email and the phone number there. Next slide, please. Okay, this is specific to North America chapter. We like to keep it exciting and refreshing and keep our members engaged. And so we are planning an upcoming field trip to the Ocean Star Museum and Education Center. There will be more about this. So just stay tuned for more information. Thank you. So this is a very good time to take our sponsors' remark and want us to welcome Chief Tunde Afolabi, who is the chairman of today and the CEO of Amne International Petroleum Company, who are the sponsor of this meeting today. A big round of applause. Chief Tunde Afolabi has over 4 decades of experience in the oil and gas industry. He was educated in geology at Franklin and Marshall College and Tulane University in the US. He worked with Texaco, Mobile, and later led Exploration Consultants Incorporated before founding Amni Production Company Limited in 1988. He's a fellow of NAPE, and in fact, a former president of NAPE 2000 to 2001. And he's a leader in several professional petroleum associations. Chief Afolabi has received multiple national and international honors, including the member of the Order of the Federal Republic of Nigeria. And he has several honorary doctorates and holds appointment as Chancellor of Ajayi Crowther University and Technical University in Nigeria. Please welcome Chief Afolabi.
Well, hi guys, ladies and gentlemen, I'm just happy to be here. This is Nappy had been, I think, my dear, and I'm glad that this young lady is picking up from the trail. So this is not my expected turnout here, but the young shall grow. Hopefully, you should be able to drum out the bushes and get your members to participate in what you do. So welcome. I hope you're enjoying yourself. Thank you.
Thank you, sir. In addition, we have over 60 attendees online as well. So we want to move on to the next agenda, which is vote of thanks from Victor Ogumola, who is also the president-elect of APJ Africa.
Yeah. Good afternoon, everyone. It is a high privilege to be given the vote of thanks this afternoon, and I want to extend our sincere appreciation to the speaker of today, Dr. Erik Scott. Thank you for such an insightful presentation. So your depth of expertise and clarities in unpacking complex geological frameworks have provided us with valuable perspectives this afternoon. And we truly, truly appreciate you for that. And as Oliver Twist, you can expect us to knock at your door at a point again. Thank you. To our event chair, Chief Tunde Afolabi, MFR, FNAPE, we are truly, truly grateful. Thank you for your steady leadership. You've been an inspiration to the industry. Personally, I've been hearing about your name for decades. I've had the opportunity to see you afar many times. So we are glad to that you did sponsor this. We are very grateful. We are deeply grateful to our event sponsor, of course, the company Amni International Petroleum Development Company, whose generous support made this technical business meeting possible. Your commitment to advancing geoscience and fostering industry collaboration is truly commendable. Thank you, sir. And we thank your team as well. At Amni, thank you, Ogabringa. So one of the executive director of Amni. And I have to do a shout out to, and I know Chief himself kind of acknowledged the role you play in this. Thanks for facilitating this for us. And of course, we look forward to your more active participation in NAPE. So finally, we also want to thank the leadership of NAPE. We got Mr. John Bosco on the line. I know in Nigeria right now, it is like 6 hours ahead. Thank you for being part of this, and we appreciate your leadership. We also thank Mrs. Olajimoke Ajayi, the president-elect of NAPE. And of course, to all our attendees, and industry professionals and leaders, researchers and students alike, thank you for your active participation and thoughtful questions today. Your engagement is what transforms a presentation into a conversation and a gathering into a community. So we truly, truly appreciate all the participants of today, both here and those that had to attend virtually. Like Jumoke said, we have over 60 participants online, and we take your encouragement as a call to action. So this is a very nascent chapter. We started about 2 years ago, and we've been working really hard to bring together our others. And personally, I'm very optimistic about this particular chapter. It's going to be the biggest chapter of NAPE. We have our students migrating here. We have our young professional coming on expatriate assignment. We have our retirees making Houston, making US a home. So it's a matter of time. We are really, really optimistic that our chapter will continue to grow. So finally, especially to NAPE, North America chapter, and I want to personally thank our coordinator for his leadership. Like the president said earlier, Mr. John Bosco, we could be putting in individual effort, but without having that right leadership at the end of our affair, all this wouldn't have come together. So I know she doesn't like to be recognized, but your leadership has been so inspiring. Thank you, Demola. I also want to thank folks that have been working behind the scene to make this happen. A lot of our volunteers, John, Dr. Ugo, many of us, of course, our moderator today. So you guys have done wonderfully well. And on the final note, let us carry forward the insights shared today as we continue to build more accurate, predictive, and resilient geological models. Once again, thank you, Dr. Erik, for that presentation. Thank you once again, and we look forward to reconvening future forums where knowledge meets action. Thank you.
Thank you, Victor. So we are actually very close to the end of our program. Before we start the post-event networking, I know we have the president-elect of NAPE online earlier, and Mrs. Olajumoke Ajayi, just a shout out to recognize you for staying up this late to be with us. And I personally want to thank Yemi. She did a lot in the background, and I've been working with her on this. And just take your flowers, Yemi. You did great. And yes, so we will take photos. And I think in the absence of anything else, thank you, everyone. It's been a great pleasure having you here today. Thanks for coming out. And we also want to thank those who are online. Thank you very much. So we will huddle here and take a photo with Chief and Mrs. Afolabi. Hi, everyone. So on your way out, we have some lunch. I almost said leftover, not leftover. They are really still intact. So please take some with you. We really appreciate that. Thank you so much.